a look for exam rewrites. This should be directly helpful for probably 90% of the class, because 90% of the class got this question wrong. Question 7. How many possible stereoisomers could be produced for the reaction below? Right. This one becomes a little bit more straightforward, because you could just go through and draw the product and count each of those possible things. So for this one, what would I expect? Positive, and then D. Okay. Within that, I should immediately note what? I have stereochemistry because the attack could have come either direction, which means in this case I don't have one product, I have two products. Okay. Now what could happen? Now the bromide could go through and attack. So I could have had the bromide attack from the top, or I could have had the bromide attack where else could the bromide attack? From the back side. Bromide could have attacked from the top, or the bromide could have attacked from the bottom. So now the question becomes, do we have copies? I mean, those are wedged and that's dash, right? So are those copies? We should be able to go through and verify each of those to decide whether they are a unique product or not. Okay. That information should get added in there to identify each of those relationships. Once those relationships have been identified, you should be able to come up with the correct answer. Make sense? So that's a lot of work for a single question. Okay. That's what I expect you to go through and do. Yay. Okay. When should you do this, by the way? When should you go through an old exam and figure out what went wrong? Every time you get an exam back. Every time. Just because you get points for it doesn't mean you shouldn't be doing it, or you should be doing it now. Right? You should always be going back and reviewing your content to figure out what went wrong, particularly in this class, because what's going to happen in this class? It's going to come back again. Okay? So you will see it again, okay? And it may even be the exact same questions. Okay? So, with that excitement, we're going to go ahead and move forward. Okay. Where we ended last week was looking at the quote-unquote obvious reaction from our enolates. Okay. The keto functional group, or really any alpha hydrogen to a carbonyl, so that is the alpha hydrogen, is acidic. Why is it acidic? Bless you. The first thing that most people would go through and say, well, it's not acidic because I have a negative charge on carbon. Right? Not a bad idea, but before you go through and draw conclusions, you should also evaluate to see if there's a structural effect. like resonance. Which of these two structures, red or purple, should I be using to evaluate whether or not the species was stable? Purple. Why should I evaluate the purple over the red? Showing how the charge is distributed, both are doing that. Why is purple more important to explaining hydrogen's acidity? It has to do with the charge. Where's the charge located in the purple structure? On oxygen. Why is a charge on oxygen better than a charge on carbon? Okay. Comes back to electronegativity. Yes, we can make the statement that it's more stable. Okay. Making that statement in and of itself without an explanation is meaningless. You have to tie that explanation to it. Oxygen is more electronegative than carbon. That's why I can remove the hydrogen from carbon, because of resonance. I can put the charge on oxygen. Okay. The acidity of that hydrogen is roughly the same as that of water. Okay. That is how insanely acidic that is. Okay. Why would it be the same as water? When water loses a hydrogen, where does the charge fall? Where does that negative charge fall? Where does it sit? On an oxygen. Where's the negative charge fall here? On oxygen. Shouldn't I expect roughly the same charge? Yeah. Okay? So, with that position being acidic, I can react it under basic or, believe it or not, acidic conditions. We'll see what happens with that in a little bit. I now have a nucleophilic carbon. Why do I recognize the nucleophilicity in the red structure but not in the purple structure? Which structure was the more important one to decide that the hydrogen was acidic? The purple. So this one's important. Okay. For, let's call it acidity. And yet when I want to decide how this molecule acts as a nucleophile, I'm not looking at the purple one. That's where the charge is most stable. Shouldn't that be the nucleophile, the oxygen? We think back to resonance, remember? The best, worst resonance structure is the one that dictates chemistry. Okay? Or the second best, however you want to look at it. Okay? The purple one's the best. That dictates our stability. When I want to know how this molecule reacts, I'm going to look at the next resonance structure. The next resonance structure puts the negative charge on the carbon. There's my nucleophile. What else could it act as? A base. Is it acting as a base particularly useful? How did I get that red carbon, that nucleophilic carbon? What did I do? How did I make that basic carbon? I removed a hydrogen. Okay. If I have it act as a base, what am I doing? I'm just doing the reverse. I would be undoing the chemistry that I started. Is it typically good to look at it acting as a base? Probably not. It may be something that's important through intermediates. Okay, so we need to think about it if we're concerned about our intermediates. But as far as reactivity goes, we don't want it acting as a base because that undoes the chemistry we just did. Okay? The standard reaction, once we've got our nucleophile, react it with our alkyl halide. Why not an alcohol? Right? Because if we look at our kind of spider diagram cheat sheet, we say Rx. Okay? CH3Br. Why not CH3OH? OH isn't as good of a leaving group. What did you suggest?
Wouldn't that give you an ether? Because the O could act as a nucleophile?
The O could potentially act as a nucleophile. Which is the stronger nucleophile? Negative charge or the oxygen? The negative charge. So our alcohol is probably not going to act as a nucleophile. Okay, so we've got an explanation. Bromide's a better leaving group than OH, so that's cool. What's the problem with our alcohols? What about the hydrogen? It's a different color. Fair enough. It could get snatched up. That hydrogen is acting potentially as an acid, as a proton donor, which means our nucleophile could be quenched by mixing it with a protic solvent. That does the reaction we just went through and did. Quenched is a valid term for how we would describe this. Most reactions get quenched this semester. Okay? So using the alcohol as our Rx is a bad idea. Okay? Because the alcohol has other chemistry than just the leaving group. It can also act as an acid. Okay? So we have to consider that when we throw in our other reagents. Kind of, sort of? Okay. This is a fun little foreshadowing that goes way, way out there, but this is a relatively famous reaction. Okay? It starts at the bottom and kind of cycles upwards. Okay? We can start with malonic acid and circle all the way back around up to that structure. Okay? This is taking advantage of that exact same chemistry. Okay? The malonic ester has an acidic hydrogen. So in the very first step, I add a strong base to make the nucleophile. That nucleophile can then attack my electrophile, and I've added an R group to my structure. The rest of the chemistry afterwards becomes a little bit more complex because that's involving the chemistry of a carboxylic, or sorry, what functional group is that? No, not ether. Ester. It's an ester. We have a carbonyl with an R group, with an O and an R group. We have an ester. The ester can then get turned into a carboxylic acid. Then what's happening is we transition all the way across. Holy crap, we lose an entire carbon structure. Okay, we can subtract carbons from the structure. That's kind of neat chemistry. There's a typo there. I'll fix that when we talk about it for reals. Okay. That can elongate our carbon structure. We get more carbons in our compound. So it becomes an important synthesis reaction for that. Okay. Have we seen other electrophiles? Yes. What was our standard electrophile that we've now seen a couple times? As a subtle hint, it is on the slides. It is on the slides once, twice, 3 times. Bromine. Bromine is a decent electrophile. Why would bromine be a decent electrophile? Draw out the Lewis structure. What do you see? If it had electrons, wouldn't it be a nucleophile?
Somebody's going to leave.
Why would somebody want to leave?
Because it's a halogen.
Kind of accept that. What's special about the bond between the 2 bromines? We don't like those 2 being next to each other? Is that what you said?
Right.
Why?
They're both electronegative, so they both form a-
They're both electronegative, so they're pulling on each other. If I say got something positive near one end of that, that could polarize that structure, causing it to break off. Okay? That leaves me with an electropositive bromine. Okay? So let's take a look at this mechanism, because you'll look at the next mechanism in a second, and that one's harder, so I'd rather do this one. What's the most reactive thing you see in this reaction here? Ooh, hydrogen. Why did you say hydrogen? Didn't I just talk about bromine and the carbonyl? Why is the hydrogen the more reactive one? It's charged. Good. So what should react with that positive?
The negative on the oxygen.
The what on the oxygen?
The negative charge?
Is there a negative charge on it?
No, I guess.
Okay. There could be, if I don't see an obvious charge, a good first step would be draw a resonance structure. Okay? When I draw a resonance, what am I moving? Any electron? Pi electrons. Do I have a pi bond? Yeah. Where should I move those electrons? I want to move them only to the oxygen. I will not move them to the carbon. Why? That carbon cannot become the negative. Nope. Why can oxygen hold the negative charge? More electronegativity. Don't break rules of our basic rules. Okay? Oxygen is more electronegative. That means oxygen picks up those electrons. And now, Ishmael, what were you saying about something with oxygen being negative?
Oh, no.
Oh, snap. There it is. What did we just look at? We looked at the first worst resonance structure. Does that tell us where our negative is? Yep. What can happen?
Attacks.
Now it can attack the hydrogen.
I'm sorry.
Go ahead, no?
You said first resonance. So shouldn't we draw all the other resonance first, or?
Turns out for this structure, there's only one resonance structure. So theoretically, yes, you would have to evaluate all of them. That's where a little bit of practice and getting used to drawing the resonance, you'll tend to jump to the most relevant one faster. Okay? Is that structure stable? No, why not? It's charged. It's positively charged. Does that carbon want to be positive? No. So what does it try and do? Not be positive by finding electrons. Does H plus have electrons?
No.
No. Does Br2 have electrons?
Yeah. Or you have to break it first.
I would have to break it first, which means Br2 would need to act first as a Br positive. Positive to positive doesn't work. Where are their electrons?
Yeah.
We just addressed Br. There's no electrons there we can use.
What about some coordination? And another pi bond in there?
No. Elaborate on the other pi bond.
Can another carbonyl, can another view come in that we had before? There's more stuff floating around, right?
There is still more stuff floating around, and that more stuff does have a potential negative charge chilling on that oxygen, right?
So we're supposed to assume there's more of
More
the
of the
original
reactant.
circle.
That there's more of the reactant. So if we don't make that assumption, you're assuming I take only a single molecule?
Yeah.
Can I react a single molecule? No. So your initial assumption that there's only a single molecule was a bad assumption outright. Okay. Which, and I'm not trying to be snipey,
No.
because I see you guys turning, ooh, yeah, no. That's legitimate. That's one of the kind of big things that we have to address in second semester. We got tons of these things floating around.
Yeah.
Okay.
This is just on paper, I guess.
So now the question. Is the oxygen nucleophilic?
Right now, no.
No, it's not. So those electrons can't stabilize the positive directly. Where else are there electrons?
Between the bond.
Bond is a good hint, but I'd like to know what bond you're referencing.
The pi bond?
No. Sigma. What sigma bond?
You're asking the wrong person, dude.
You provided the answer. Is there potentially a subtle hint already on the slide referencing what the ketone can potentially do?
Oh, okay. Hydrogen.
What hydrogen?
Hydrogen between the carbon.
If we're going to get at our nomenclature with this would be the hydrogen at the alpha position on our ring. Those lone pair electrons. What happens? The bromine is not negatively charged. If anything, the bromine is positively charged. It's an electrophile. Okay? You can talk to me after class. Every time we've seen bromine, it's an electrophile. Bromide, which isn't there yet, is a nucleophile. There's no bromide. It's only bromine. Okay? So now what can happen? We could look at resonance, showing why that was a reasonable thing to go through and do. Okay? We have a resonance stabilization of that structure. That resonance stabilization helps to explain why we were allowed to do that. It also sets us up with what? A nucleophile. What did we say was also floating around in solution? Bromine. Bromine acts as an electrophile because of that weak bond between two electronegative elements. When it gets near that negative, we can polarize. There's our reaction. And what do we end up with? Does oxygen want to be positive? No, so what could pick it up? We'll accept a couple answers and kind of work from there. We could show the bromide picking up the electrons. I already heard someone shouting no. Shouting was a relative term.
Could another negative, could another blue with the red oxygen pick that oxygen up?
So, someone shouted no. Why did they say no to the bromide? You'd form HBr as a product. What is the problem with HBr? It's a strong acid, and by definition, strong acids just completely dissociate. So it doesn't make sense to have bromide be the one to pick up that hydrogen. Okay? So what else has electrons floating around that could possibly pick that up?
The step before that.
Okay. I would argue not the step before that, but all the way down here in blue, right? I think that's what you're referencing, is that?
Well, if we're forming that, go up. Go over, please. Yep, it's stop. Right there.
Yeah.
Okay. If we're forming that, are there going to be a bunch of those?
So those could also be floating around in solution. Ultimately, what those are is a slightly unstable form or a less stable form of this species. Okay, so the concentration of those is very, very limited. So it's probably not the best thing to have shown to pick up the hydrogen. Having your starting ketone pick it up? Yeah. Okay. My argument would be to completely dodge that altogether. And instead of showing even Br, whoops, B with electrons, B for base. I don't care what basic species picks it up, but something basic picks up that hydrogen to finish this mechanism. What could that base be? It could be starting ketone. It could be bromide, generally frowned upon, but it could be that. It could also be water. Where did the water come from?
It's in the reaction.
It's in the reaction. Okay. Likely, how did we get the H plus in there? Probably in an aqueous environment. That's where it came from. Okay. Or it came from solvent, ethanol. Or it came, the worst case of all worst cases, as part of the workup for the reaction. Okay. Which is rarely listed into our reaction dynamics. Okay. So don't stress on what the base is specifically. The one thing you should worry about is what is that base not?
Strong.
It is not a strong base. Why is it not a strong base? I'm in acidic conditions. Okay? That is the biggest reason behind it. Okay? That one you have to watch out for. Okay? This is why I almost always dodge the bullet by just saying it's a base, and then I don't have to worry about it. As long as I don't put a minus sign on it, it's usually acceptable.
What if you just add a second step?
You could add a second step down here saying workup. Yeah, that's just rarely done.
And would you also add a bromine on the second beta carbon? What's stopping them from doing it again?
You mean going over here? Okay, that's a really interesting question. Okay, to that point, take a look at our summary of reactions going straight up. Under acid conditions, what do I show?
One bromine,
One bromine. Under base conditions, what do I show?
one bromine.
One bromine. What does that say underneath it?
No monosubstitution.
No monosubstitution, meaning I'm showing the basics of the reaction, but I'm actually saying
One bromine.
doesn't do one. Did I put that under the acid? Why not? It only does one. So why does it not go to the other side? Fair point. Can I erase everything there? Is that a yes? Let's draw that product out. And it's only a fair point because I'm going to make you do much worse on the next page. Okay. For this to continue, what has to happen?
Have to have a strong base.
I have to have something to remove that hydrogen. Okay? I have to have something basic enough to remove that. Okay? What that's going to come back to is looking at our conditions. Is that hydrogen more acidic than where it started? Sorry, we're under acid conditions. Okay? With those acid conditions, that's going to make these hydrogens more difficult to be removed.
Why can't you just do the same thing before? Move the double on the pylon up and then knock it.
Is the structure as stabilized with a bromide? No. Okay. That bromide, by being added, now makes that structure less likely to give up those hydrogens. What happens when we move to the base conditions? Okay, so when we went through and did that mechanism, tons of protons floating in through there. And notice that to get our active species, we still needed a negative charge. That negative charge is very hard to form under acidic conditions. Why? There's protons everywhere. We would expect it to fully protonate. It would quench. Okay? As soon as I put one bromine on, that now shuts that reaction down and makes it even more difficult for it to go through and react. Why? What's our very first step? It just clicked, sorry. Our very first step with our starting material was to do what?
Resonance.
We did not form the enolate right away. Resonance isn't a step that helped us predict the chemistry. It had to react with
Bromine. Or
the hydrogen. I had to protonate up here at the top. Okay, that had to happen. Is that as likely to happen with our product now?
Wait, what do you mean?
It says yes, but
yeah.
So what are we saying? This black structure, is it more or less basic than the purple structure? Because remember, our first step is to protonate
In acidic conditions.
under acidic conditions. Which structure is more basic, the black structure or the purple structure? Why is the black one more basic?
You don't have the room.
bromine induction.
The bromine is doing an inductive effect, pulling the electrons on that oxygen into the structure. If the electrons move into the structure, can they react with the hydrogen? No. So under acidic conditions, we only get one substitution, because as soon as we put a bromine on, we've now shut down the reactivity of the molecule. Yep, flatlines it. Yep. Okay. What happens if we now change the reaction to basic conditions? Okay. This is going to get a bit weird here, so let's make this a little bit easier. Explain why this forms. Take a couple minutes, draw some stuff out, see what you can come up with. If you got questions, you can raise your hand. Again, remember, we've changed the reaction now. It's now under basic conditions. What's our first step going to be? I'll give you the first step under acidic conditions. Is there H plus? So let's go ahead and come back. The most reactive thing is our hydroxide. The hydroxide attacks our positive hydrogen. It could potentially directly attack our carbonyl. We will be talking about that in the next unit. You can hold off on that. It doesn't work. Okay, short story, long story short. There we go. Long story short, it doesn't work to attack that carbonyl. So, attacks the hydrogen. We form our enolate. The enolate can come out, react with our bromine, and we attach the bromine. Everybody agree? Say no.
I don't like that.
You don't like which? Me telling you to say no?
No, I don't think the pylon should attack.
We're missing a carbon too.
Okay. Biggest issue first, we're missing a carbon. This reaction, it is insanely common for students to delete carbons. There's an extra carbon at the end. What happened to it when I drew this arrow? I somehow just lost it and it disappeared. Make sure you don't make that mistake. You need that extra carbon there. There's our bromine. Okay. To the question of you don't think it should attack the bromine, which part? The carbon side or the bromine side?
Yes.
The bromine side. We've proven bromine reacts in multiple cases where we have an electrophilic bromine. Okay. So like it or not, bromine's an electrophile. Okay. At no stage can we show that's not the case. It's always an electrophile. When we go to the other position on whether or not that hydrogen should be removed, am I allowed to form that negative carbon? Is that a valid structure in red? What do you mean not with oxygen there?
Because then you're going to have resonance.
We have resonance. What does the resonance do to that negative carbon? It stabilizes it, allows it to exist. Okay? So there's the possibility that what you're complaining about is you don't like the pi bond coming out immediately like that, in which case show the formal resonance where you have the negative carbon doing the attack. Okay? If you don't like that hydrogen is acidic, to form that structure in general, that's a whole other can of worms, and that unfortunately is going to go back to the basics of acid-base chemistry. Okay? The last thing that we can do with that, which really, really does suck as an explanation, does this happen? This reaction, does it happen? Yes. Period, full stop. It happens. Okay. The question would become, how does it happen? If we start with a neutral carbon that's fully saturated with its octet, it can't react. We're looking beginning to end. We have to lose a hydrogen. We have to gain a bromine. Okay. Are there other ways that we could potentially explain what happened? Absolutely. We could look at radicals. Yeah, I thought you'd like this way better. Okay. We either go to radical mechanisms or we go based off of electronegativity and stability of charges. Those are really our only two options. When we try to decide which one was the more correct option, how do we figure that out? We go to lab and we test it in lab and we see what species show up. One of the things that we find when we test this lab, or one of the things that we don't find, is any existence of a radical. If there's no existence of a radical, what mechanism does that mean has to be true? Or is most likely true? The one we're looking at. Yes?
So sometimes the BR splits up and forms a radical, sometimes it doesn't?
Yep.
And it just depends on what you're doing.
Depends on the reaction conditions. Exactly right. So it's going to come from what causes it to react. When bromine acts as a radical, what causes it to react as a radical? In all of those reactions, when does bromine react as a radical?
Oh, like,
Light. It's the very first thing that happens to cause the radical to form. Is that the very first thing that happens in this mechanism? Nope. I'm looking at other conditions initiating our reaction. Okay? Those other conditions show charge, which would suggest that charge should drive the reaction, not radicals. Okay? So it's looking at a homolytic versus heterolytic bond cleavage. Okay? The conditions help dictate that for us.
So when I was doing on my own, I didn't do the resonance.
When I went through and did I show the resonance first?
Yeah, you did the purple one, right?
I see what you're saying. So you just removed the hydrogen and went straight to the red structure?
Yeah.
Yes.
Is that potentially dangerous?
Nope.
Okay, because that makes more sense to me than the purple did.
Yeah. All that's going to come down to is where we see those bonds breaking and forming. You can jump from that very first stuff in black to the red structure, okay? Or you can show how it's ultimately stabilized better in the negative. If you're asked for a mechanism, which of those two structures should you show, red or purple? Trick question. Both. You have to show both. Mechanisms, you're required to explain why something happens. That explanation, resonance. Okay? We have to see that evidence to explain why we get it to occur. Okay? Why did I not fully show the resonance? Because the question I asked wasn't necessarily dealing with that. The question I asked was, how did we get 3 bromines on there? We've only shown 1. What is the difference between this purple structure and our starting black structure? Why is the purple one more acidic? Okay. That bromine is now inductively withdrawing electrons, making the remaining hydrogens more acidic than what we started with. If they are more acidic, what happens? Given the black structure of the purple, which one reacts? The purple one. It removes a hydrogen to add another bromine. So we'd have now a second product. Is that product more or less acidic? Even more acidic. Why is it even more acidic? Because now there's 2 bromines on it. There's now twice the inductive effect. The blue structure is even more acidic than what we started with. So under base conditions, we're going to get this substitution going until all of our hydrogens are gone. That's where it gets us the structure that I've got drawn up above. Everybody see that? From the other side?
Yeah.
How many bonds are showed to that other carbon?
No, sorry, the other carbon that's attached to that carbon.
Good question.
You know what I'm talking
I got you. I think I got you. That hydrogen?
about. Yeah.
Why can't that hydrogen be removed?
Too far away.
Don't quite accept too far away.
Too much dark.
No.
Don't you always take from the alpha carbon?
Why do we take from the alpha carbon?
Because resonance.
Resonance. We're putting the negative charge in our conjugate base on an atom that can hold it. Okay? If we evaluate that position, when I remove that hydrogen, I now have a negative charge here, right? I have a negative carbon. Remember where we first started this? You're like, you can't remove the hydrogen from that alpha position because that's a negative carbon. That's bad. And I said, well, what if we look to the resonance structure? Okay? Well, you're now making the exact same argument. Fair. What's the resonance structure for that?
There's
There isn't one. Which means if I remove that hydrogen, I'm making a negative carbon. Are negative carbons stable? No. That structure is not stable, which means that hydrogen was not acidic. I can't remove it. Okay? So very good question. Okay? Because typically that gets asked on the exam when I can't do anything about it. Okay? So we go through that reaction and we fully saturate with bromines, and we would suggest or think that that would be our final product. Okay? And of course, when we go through and clear everything, can I clear everything?
So if
So
you
no.
had like a ketone instead of that nice, would you get 6 bromines?
If we switch that, would I have 6 bromines in my final product? Yes and no. We'll get to the yes and no here in a second. The no part is I'm not positive. Okay. But what we could do is do this. Okay. Now I would absolutely be able to answer that. That's going to be 5 bromines. Sort of. We still don't get that because what happens under these conditions? Did we end up with the tribrominated product? You're like, well, yeah, it's because it's written up there. Remember how I asked, can I erase everything? Yeah, can I erase everything? Yeah. What? What happened to the carbon with the 3 bromines? It left. Is carbon a good leaving group?
That one.
Why is that one a good leaving group?
Because it's positive, slightly positive.
If it was positive, is it a good leaving group?
Yeah.
What do leaving groups have to do? Leave. How? What are they doing by leaving? Stabilizing what charge?
Negative.
The negative. They're taking the electrons with them. That carbon is not positive. Okay? It's coming off as a minus. Why would that negative carbon be stable? It has an inductive effect of all of those bromines. That is now actually a decent leaving group. Okay? For it to leave, though, something must stabilize the structure that's left behind. What could possibly stabilize that carbon? What charge is that blue carbon? Positive. Is there something negative floating around in solution? The hydroxide?
Was that just implied?
It was not implied. It's right there.
Is it an acidic condition?
In the end result, what did we end up doing here? A substitution reaction. Yep. We did all sorts of fun things with this one. If you break down each of those steps, we started with an acid base, okay? An acid base which we might have a thin argument for being an elimination, but ultimately it's an acid base. We then did a substitution to put bromine on. We then did another acid base to do another substitution, another acid base to do another substitution, and now what's happening is our hydroxide is attacking that carbonyl carbon. Have we ever shown a negative species attack a carbonyl carbon? I don't think so either, because that's the next unit. Okay? We haven't shown that happen before. That is now a nucleophilic addition. The exact mechanisms we'll look at in the next unit, and ultimately actually 2 units out, because this one's special, because not only are we doing a nucleophilic addition, we are also eliminating a molecule from the structure. This is a nucleophilic addition and elimination. This is setting up foreshadowing for our 3rd unit. But the chemistry that is happening here is ultimately one of substitution. Okay, at its simplest level. And we would form that structure and CBr with a negative charge. Okay, let's get some questions.
So that carbon in the red structure, that's slightly positive?
That is slightly positive because of the bromines. You can't call it positive because what charge is it?
No.
Wait, are you talking about the carbonyl carbon, Mo, or are you talking about the one attached?
The carbon with the bromines.
The bromine.
Yeah.
Okay.
It is partially positive because of the withdrawing effects of the bromines. We can't call it positive because what does it do as a leaving group? takes the electrons, what charge is it? It's negative. Right? That negative charge is stabilized by an inductive effect. Right? But it is not positive.
So only under basic conditions can
Nope. Under basic conditions, we do multiple substitutions. Okay? We can't control it. Okay? That's what you need to go. The next part on this is that if you have a methyl carbonyl or a methyl ketone, okay, this was a CH3, so this is a methyl. This here is a ketone. If I have a methyl ketone, we get this bizarre chemistry coming out. Okay, which is an ACS question, which we'll look at in a second. So everybody's okay with what's drawn in blue?
So, the basic conditions in alpha halogenation. Step number 1, form the enolate,
Yeah.
then do an SN2 attack.
Yeah.
But why do you say multiple substitutions?
Because what happens with our product? The product of that substitution is more acidic than our starting structure.
Okay.
So we are more likely to get another enolate. That enolate is more reactive, but it continues the cascade.
Second?
All right, so I'll answer the question, but if we started with what you actually have drawn, if you erase the two methyl groups on the left, would we go to the...
Oh, that's interesting. It's not erased on my screen.
Oh, well, no, I like to erase, that was my question.
Damn it.
So, sorry. If it is erased, it's more stupid, but is it the right carbon or the left carbon that we're doing that? Because wouldn't...
We would get brominations on both sides. So you'd get the 5 bromines that Mo was asking about. One side ejects and it gets replaced with OH. What happens to the other side? Those would be bromines. So the net effect is not 5 brominations, but 2 brominations. So we'd have to be careful with how we count and looking at our final product. Not to call anybody out from the tutoring session. What functional group is this? A carboxylic what? Under what conditions? Basic. Is this mechanism correct? Nope. What has to happen? You would have to deprotonate. The electrons go back to our oxygen. Here's the driving force for this reaction. Does this mechanism ever end? Yes. Once we have this structure, we now have a stabilized negative. Why would this step happen? Are you really happy with a negative carbon? No. What does that need to do? That needs to remove that hydrogen so that we get a stable product. Is that our final answer? No. So what the hell?
Step 2.
Why do we have step 2 of adding H3O+? Because we have to protonate that final stage. Okay? For those of you going, God, I've never seen that before. You have. All of our alkyne chemistry does the exact same thing. Okay? When we go through to make alkyne nucleophiles, okay, since I heard a when, let's just clear the whole thing. Let's do it this way. If I do NaNH2, what is the product of this? An alkyne. Only partially correct. It's an alkyne with a negative charge. Why? The alkyne is more acidic than the starting alkane or alkene. Under the base conditions, we deprotonate that hydrogen. What if I want just the alkyne? Step 2, I have to add H3O+. Now our hydrogen goes back on. So if you've ever seen a reaction where you're like, why did they add that H+? It is typically because your reactant intermediate reacted with your final product, generating an unstable intermediate that had to be quenched. There's your H3O+. That would be an acid workup, yep. Okay. So, once all 3 alpha protons have been removed and substituted, CBr3 becomes a decent leaving group. Okay. It's not the greatest, but remember we get stabilization of resonance with our conjugate base. Right? So all's good, and we end up running that goofy reaction. Where does this tend to show up? Which compound will give the yellow solid HCl3 when mixed with iodine and sodium hydroxide? What the hell are they saying? Okay. Well, they're saying iodine and sodium hydroxide. So if we made an edit to the above reaction, I got sodium hydroxide and I have I2. What is the difference between I2 and Br2? They're both halides. So what does that mean happens to the chemistry? Nothing. They do exactly the same thing. So when we run this reaction, what happens? We kick out the leaving group Ci3 with a negative charge. What then happened to that negative charge? Picked up a hydrogen, and I have HCl3, also known as the HCl3 shown in ACS question. Why do we look at this reaction? It gives a characteristic yellow solid, and it gives it in the matter of seconds. If and only if this reaction can proceed. What allowed this reaction to proceed? It's not acidic, so no. The deprotonation, yes. Where? At our alpha position in our starting ketone needed to have how many hydrogens? 3, so that I could get 3 iodines attached. So I needed what kind of a functional group there? Name that alpha position for me. It is a methyl. Okay. That methyl happens to be located next to what? The carbonyl carbon. Name that functional group. A ketone. Okay. So what they do is they list 4 structures. One of them is a methyl ketone. The other ones probably have carbonyls in them and are just there to be confusing. You would have to know this chemistry to answer that question. It comes from effectively a lab question. It's a classification test because it happens so fast. Okay. So if you see reference to that, that's what they're talking about, a methyl ketone. Okay. Yay, tests. Our Enolate Chemistry. Okay. I would really kind of like you guys to work through the mechanism here, but I'm going to show it for you on the right structure. So since I'm asking for an enolate, okay, the enolate is a negatively charged, so I'm effectively asking this to run under basic conditions. The basic conditions tend to be a little bit easier to see. So I'm going to go ahead and take the hydroxide, and I'm going to have that react with the acidic hydrogen. Okay, since the black one is closer to the oxygen, that's got to be the acidic one. So I'm going to draw out the product. And I've got resonance to go through to show to stabilize. Those of you that are drawing, pause and think before you start drawing. What do you mean? Oh, okay, sorry. Yeah, it can be confusing with all the lone pairs. Let me just get rid of those. What do you mean? What's wrong? That is a very good response. I'm glad that you guys are all cringing. Okay? Why is the other hydrogen the acidic hydrogen? Okay. Isn't that black hydrogen closer to the electronegative element? Shouldn't it be more acidic? It's not an alcohol. That functional group is an aldehyde. That hydrogen is not acidic at all. Can I do resonance? Okay. The whimpering no was nice. You are correct. No, you cannot do resonance. Why? Triple bond to oxygen isn't the problem. You've exceeded the octet on the oxygen. You can't do resonance, which means you are stuck with a negative charge on carbon. Is that stable? No. Okay? So this goes back to our rules for evaluating acid strengths. You need to think about the structures, not just say, well, it's inductive, so it's going to happen. Induction is the last thing you should be evaluating when you look for reactivity. Our base is going to come through and remove the hydrogen over here. Okay, because there was a request to go a little bit slower with my arrows. We'll go ahead a little slower with that. Okay, doesn't that make a negative carbon? Isn't that just as bad as what we just drew? Why is this now okay? Because now when I go through and show the structure, I can put the negative charge onto the oxygen. Right? We're moving the electrons. You have to be very careful that that is what we're referencing in each and every single one of these stages. You pick that up with practice and skill of looking at how the electrons move. Your curved arrows are the instructions. If your curved arrows are wrong, you're following the wrong instructions. You're ultimately guessing at your structures, which is why you get questions wrong. The arrows are your instructions. Do not forget them. Start with them. That's what tells you how to draw out your answers. Okay? So, there we go. There's one. If we went through and did it on the other side, after a couple mechanistic steps, what do we end up seeing? We'd get a negative charge on that carbon. What's special about that one? Resonance. How much resonance? Double resonance. Which one's more stable, left or right? Fair answer. Different question. Which species is more stable, the left structure or the right structure? I know. Okay. Our double ketone is more stable than the single aldehyde because we get 2 resonance contributors as opposed to 1. Now, what does that mean? The acidity of the structure on the left is significantly higher. How much higher? The pKa drops to about a 9. The pK of the aldehyde or acetaldehyde is about a little bit higher than water. Okay? 9 acidity. We're now actually becoming an acid. Carboxylic acids have a pH of 4. Okay? We're starting to get into that general sort of area. Okay? The next part of this is what base do we choose to use? Okay? Well, there are 3 primary base categories. Okay? Negative oxygens, negative hydrogens, and negative nitrogens. We won't look at negative carbons because they're confusing. We will see them a little bit later. Okay? If I use a negative oxygen, okay, how would I predict that equilibrium to lie? Towards the right or towards the left? Whichever one's more stable. Fair enough. How would we evaluate which one's more stable? What do I need to look at? Of what?
Where the chemistry is occurring.
Where's the chemistry important?
At that compound.
I should be evaluating those 2 structures. Why? They're the ones that are charged. That's where our primary chemistry is located. Okay? Arguably the top one, I shouldn't even be looking at that one. I should be looking at that structure. What is the difference in reactivity between our oxygens? Which oxygens do you think I'm talking about?
The one in ethanol.
So that oxygen versus
Versus the,
why those 2?
they're both.
Those are the ones that are charged. Again, the rest is extraneous information. Focus where the chemistry is. What do you think the difference in reactivity between those is? It's about the same. Do we expect an equilibrium reaction? What does equilibrium mean? Forward and back are the same. If my product and reactant are roughly the same energy, do I expect an equilibrium? They're the same energy. Yes, yes I do. 152. Yay! What about the next one? What should I be comparing? Oxygens? I should be comparing hydrogen. Why am I now looking at hydrogen and not oxygen? Because that's the one that's charged. What am I comparing that to? Oxygen. Which one's more stable? Oxygen. Is oxygen more stable than hydrogen by a lot or a little? A lot. Should I expect an equilibrium? No. Which means this reaction is not reversible. Reversible. Not equilibrium. That works. Not reversible versus reversible. Irreversible versus reversible. Those words sound familiar. They sound an awful lot like the words that we use to describe kinetic and thermodynamic products.